Welcome students, we are back with another lesson. So in our last class we have discussed binding energy. So what is your binding energy? The amount of the energy required to break the nucleus of the atom into its constituent nucleons, such as the protons and neutrons. This amount of the energy required to break this nucleus is known as your binding energy. Now in today's class, we will derive the expression for the binding energy and then we will derive the binding energy per nucleon. So consider a nucleus. This nucleus has Z number of protons and A minus Z number of neutrons. Then its mass defect can be written as this formula: delta M equals to the number of protons multiplied with the mass of the protons plus number of neutrons multiplied with mass of the neutrons minus the mass of the nucleus. Fine, so I can use this expression here. Z is the number of protons, MP is the mass of the proton, A is the mass number, Z is the atomic number, A minus Z gives us the number of neutrons, Mn is the mass of the neutrons, and M capital N, okay, this one is the mass of the nucleus. So small n stands for neutrons, capital N will stand for nucleus. Fine, don't get confused. So let's give this equation some number. Let us say this is my equation 1. Fine. Okay. So that you don't get confused with this N and Mn. Okay. I'll define this Mn. Fine. So Mn is the nuclear mass. So we know that this mass defect gets converted into the binding energy. Fine. So from your mass energy equivalence relation, that is your binding energy is equal to the mass defect multiplied with C square. Fine. So this is the famous Einstein's relation. What this relation says is that a given quantity of mass can be converted into energy, or a given quantity of energy can be converted into a mass which is moving with a velocity c. Clear? So this is your mass energy equivalence relation. It helps the conversion of mass to energy, energy to mass. Clear? So here I can substitute this value of mass defect. This is the expression of my mass defect. I can substitute this expression here. So if I substitute the mass defect formula here, the binding energy can be written as ZMP plus A minus ZMN minus mass, nuclear mass, whole thing multiplied with C square. So this is the binding energy expression for the nucleons inside the nucleus. So the amount of the energy by this nucleons, that is your protons and neutrons, are binded together to inside the nucleus. This is your binding energy, which can be given by this expression. Fine. So this is the binding energy. Fine. Now if you look carefully, just like the nucleons, just like your nucleons which are binded to each other inside the nucleus. Okay, listen very carefully. Just like the nucleons, your protons and neutrons, which are bounded towards each other by binding energy, similarly, your electrons which are revolving around this nucleus, they should be always binded to the nucleus, isn't it? This electron is not moving away from the nucleus, isn't it? It is revolving around the nucleus, And since why is it around the nucleus? Because it is binded with the nucleus. So the energy with which this electron is binded with the nucleus, we'll call this energy as the binding energy for electrons. So to write this binding energy, I will write this binding energy, fine, EB, which is your binding energy. But since I'm considering for the electrons, so I'll mention an electron. This binding energy is for a electron which I have showed here. Clear? See, I'm not using the same notation. Okay, for this, for the nucleons, I'm using only delta EB. But if I'm considering for the electrons, I'm writing the binding energy for electrons. Fine. So this binding energy can also be written as the sum of the individual particles. Okay, so here you have a nucleus, and this nucleus mass is given as Mn. Okay, this is your nuclear mass, plus the next particle is your electron. Okay, so this is your electron. This electron's mass is Me. Fine. So the mass of the individual electron is Me. Now how many electrons will be there? There will be the number of the electrons will be equal to the number of protons. If there is one proton, then there will be one electron. If two protons, then there will be two electrons. So I can say that the number of electrons also is Z, which is your atomic number. So the total mass of the electron can be written as Z, the number of electrons multiplied with the mass of individual electron. Fine. So this is the mass of the nucleus, and this is the mass of the Me is the mass of the electron, and Z is the total number of electrons. Fine. So this is the sum of the masses of the individual particles minus the mass of this element, the mass of the atom. And this mass of the atom is given as the mass of the element Zxa. Fine. And to convert it into energy, what you will do? You will multiply this mass defect using this Einstein equivalence relation. You multiply the mass defect with c square. This gives us the energy equivalent quantity. So here the mass defect of the atom is given by this quantity. To convert it into the binding energy of electron, what you do? Multiply it with c square. Fine. So far we have derived the expression for the binding energy of nucleus, and we have derived the binding energy for the electron towards the nucleus. Fine. Now experimentally, the binding energy of the nucleus will come around somewhere in the range of kilo electron volt, and the binding energy of the electron is in the range of electron volt. So can you see here how much is the difference? So kilo means 1000. This is 1000 electron volts, whereas the binding energy is just in electron volts. Can you see? This is the binding energy, the small energy which is inside the nucleus is 1000 times bigger than the binding energy outside the nucleus. Okay, I've showed with the wrong arrow. I'll show with the correct arrow. So from here you can see that the energy with which this electron, which is attracted by the electrostatic force towards the center, towards the nucleus, is very small as compared to the energy between the individual nucleons. Fine. Can you see? So this binding energy of the electron is so small. Okay, it is so small that I can ignore this term. I can ignore this binding of energy of electron when I'm considering the binding energy of nucleus. Fine. It will be just like It will be just like, suppose if I'm giving 1 electron volt to break this nucleus, then I have to apply 0.01 electron volt to remove this electron from this atom. So can you see, this energy is so small. This energy is so small that I can ignore this value. Instead of using the binding energy of electron, if I simply supply the binding energy for the nucleus, the electrons as well will be removed. Clear? So this energy is so small that we can ignore this value. So this binding energy of electron is so small that I can equate it to 0. Fine. So your binding energy of electrons approximately equals to 0. So what is the expression of the binding energy? Let me write down here. So I can write the nuclear mass plus total mass of electron minus the atomic mass multiplied with c square equals to 0. Now look here very carefully. This is the first term. This is your second term. Now, if you look at your second term, can your second term, which is your speed of light, will it ever be equal to 0? The answer is no. The only possible case is that this part, which is inside the bracket, this part has to be 0. So I can say the nuclear mass plus the total mass of the electron minus the atomic mass should be equal to 0. And when this case is possible? This case is possible only if the nuclear mass plus total mass of the electron is equal to the atomic mass. Or if you look here, there's one more way to show. If I send this quantity to the other side of the equation, what will happen? This negative will become positive. So the nuclear mass plus the total mass of the electron is equal to the atomic mass. So when this condition is satisfied, this term, the binding energy of the electron, will be 0. Fine. So from this expression, we can find the expression for the nuclear mass. To write the expression of the nuclear mass, what you can do is send the total mass of the electron to the other side of the equation. Fine. So from here, I can also write my nuclear mass as the difference between the atomic mass and the total mass of electron. Fine. So this is the expression for the nuclear mass. Okay. So let me give this expression some number. Let me give this expression equation 3, this one as equation 4. Fine. So now I can equate this equation 4 in my expression 2. Here I have a nuclear mass, isn't it? I can equate the expression for the nuclear mass here. So this is your equation 2. Now let's substitute this expression here in the nuclear mass. Fine. So I'll get somewhat like this. Now look here. There is a negative sign. Okay. So if I multiply this negative, this term becomes negative, and this term minus ZME, this term will become positive. So my binding energy in terms of the mass of protons, in terms of the mass of neutron, in terms of the atomic mass, in terms of mass of electron, can be written as ZMP plus A minus ZMN minus atomic mass plus the total mass of electron. So if you look at these two terms, you have a Z and a Z common. So let's take this Z common first. So if I take Z common, what I'm left with? Mass of proton. And if I take Z common from here, I'm left with mass of electron plus mass of electron plus the total number of neutrons multiplied with mass of neutron minus the atomic mass. Whole thing multiplied with c square. Fine. So this is the expression for the binding energy of the nucleons inside the nucleus. Here you have expressed this binding energy in the units of the mass of the proton, mass of the electron, mass of the neutrons, and atomic mass. Okay. We could have used this expression also, and we can use this expression also. But most of the times in your numericals, in your question, in your numericals, okay, they don't give this nuclear mass. Okay, they don't give the nuclear mass. Rather they give you the atomic mass, or the atomic mass you can write down using your memory. Okay, you can write down this atomic mass. Most of the time this atomic mass is given, and they give you only the number of this. Okay, the number, what are the number of, what is the atomic number, what is the mass number, they will give you this quantity, and they will ask you to calculate the binding energy. Fine. So based on the memory, or the constant which they will give in the question, like the mass of the proton is a constant, mass of an electron is a constant, mass of a neutron is a constant, this constant value will be given as well. Fine. Apart from this, they also give the atomic mass. Okay, even if they have not given the atomic mass, you can always write this atomic mass yourself. Okay, so for to solve the numericals, we will use mostly this expression instead of this one. Fine, because in question they don't give the nuclear mass. Fine. Okay, and sometimes they also give the mass of hydrogen atom. Okay, they give mass of hydrogen atom. Okay, so you can write down like this. Okay, there's a special case also, like consider your hydrogen atom. This is your hydrogen atom. Inside the hydrogen atom you have a proton and you have one electron. So what will be the total mass of this hydrogen atom? The total mass will be the sum of the mass of the electron and the mass of the proton. So the mass of the hydrogen atom is the mass of the proton plus mass of the electron, which I can replace it here. So I can write this binding energy also as Z times atomic number times the mass of the hydrogen atom. See, I've replaced this one with mH plus the total mass of the neutrons minus the atomic mass, whole thing multiplied with c square. So this is also the expression for the binding energy. Fine. So that's it for today's class. Thank you. And if you have any confusion, please feel free to ask. I will re-explain it to you again. And in our next class, we will complete this derivation. Okay, we will derive the final expression, which is the binding energy per nucleon. Right? Or we will define the binding energy per nucleon and write down the expression for it. Fine. So that's it for today's class, and again, thank you.